So, first one. Let's calculate the divergence and also calculate the curl of two vector fields. Now, on a side note, right now divergence and curl don't seem very, for lack of a better word, exciting. But they're going to be like, whoa, that's so cool, later. So, but for now, all we have to remember is what does divergence mean? That's del dot f, which means it's the sum of the partial derivatives. So that's, take the derivative of the first entry, derivative with respect to x, derivative of the second entry with respect to y, derivative of the third entry with respect to z. So here we have that the divergence is going to be, come to the first entry, take the derivative with respect to x, easy. Cosine of the y is a constant. Okay, go to the second entry. Ugh, it looks intimidating, but we're taking derivative with respect to y. That term's going to go away. So the next entry is 3y squared. That's root of y cubed. Go to the last entry. There's no z. We're taking derivative with respect to z. We get cosine of z, and we're done. No, it's a function. It's not a vector valued function. It's just a normal function. So when you take divergence, you should just get a normal function. So the next one, the curl. Now curl is del cross f. So here you have to remember del, that's your partial derivatives. And when you're doing cross product, I like to just actually do the cross product. So we're going to go ahead and carry out this cross product. So I, j, k, the partial derivatives. So partial x, partial y, partial z, and then the function sine yz minus x, cosine xz minus y, e to the xy minus z. And so we start working our way through, go down diagonals, take the derivative with respect to y of e to the xy minus z. That's x e to the xy. This is in the I direction. Take the derivative with respect to z of sine of yz. That's going to be y cosine yz. That's in the j direction. And then take the derivative with respect to x of cosine of xz minus y. So that's going to be minus z, because we're taking the derivative with respect to x, sine xz in the k direction. Got to go the other way. So now going the other way, derivative with respect to z, cosine of xz. That's going to be minus. But because we're going the opposite way, it's another minus. So it's minus sine of xz. And don't worry, I didn't forget that we need to do the chain rule times x. And that's in the I direction. J, partial x, e to the xy. But again, minus. So that's going to be minus y, e to the xy. And then k, partial y. So that's going to be, the x goes away. And then we get cosine yz times z. That's in the k direction. You could leave it like that. You could also simplify and say, okay, that's x e to the xy plus sine of xz times x, comma, y cosine yz minus y e to the xy, comma, and minus z sine of xz minus cosine of yz times z. All right, so divergence and curl, they're fairly straightforward. Just remember your definition and you're okay. Convert, but do not evaluate the following integral. We're going from negative root 3 to positive root 3, negative root 3 minus y squared to positive root 3 minus y squared, and then 1 to the square root of 4 minus x squared minus y squared of x squared plus y squared dz dx dy. So we kind of have to understand what's happening. So remember, integrals work up. So we have negative root 3 to positive root 3 dy, which means if we were coming here into the xy plane, we're going from minus root 3 to plus root 3. Then we go into our next layer, and that's going from minus root 3 minus y squared to plus root 3 minus y squared. And again, these are x bound, so this is x equals. And if you work that out, what you get in both cases is this corresponds to x squared is equal to 3 minus y squared, or x squared plus y squared equals 3. So in other words, the plus square root of 3 minus y squared is the right half. The minus square root of 3 minus y squared is the left half, which means in terms of the xy plane, you're dealing with a circle with radius square root of 3. Now, let's talk about our third dimension. This is z. So z says what? Well, come in here. You have your circle down here, which is where your region is over. And now, the top of your region, you start not at the xy plane. You start here at z equals 1. And you go up until, so we can go up to our circle, and we go up until we hit the square root of 4 minus x squared minus y squared. Now, the square root of 4 minus x squared minus y squared, that's actually a very nice shape. That's a sphere. So it's like we took the top part of a sphere off. So here's our region. Now, you might be getting just a tiny bit nervous at times like this and saying, am I going to have to be able to draw 3D shapes? Well, I'll tell you what. You won't have to draw a 3D shape on this test. If you do have a problem with the 3D shape, and it's important to know it, we'll give you the shape. So that's the good news. The bad news is you still might have to figure stuff out. But at least you won't have to draw. All right, so there's our picture. Now, we want to convert this into cylindrical and into spherical. Once you're doing conversion into cylindrical and spherical, the best thing is to sort of like look at a cross-section, because that can really help illustrate what's going on. So I'm imagining cutting down, like I'm cutting straight down the z-axis. So I have my z-axis, and down here, I like to call it r, because it doesn't matter which direction I'm in, I'm always going to have the same shape. So what I see is the top part of it, here's my circle, because when I cut a sphere straight down, I'm going to get a circle. So there's my circle, and then I see this line, z equals 1. So there is z equals the square root of 4 minus x squared minus y squared. And so I can imagine that really my shape is formed by spinning this region here. And this will help me understand how to set things up. So now we are ready to talk about cylindrical coordinates. So this is our r, theta, z. Now for r and theta, we look in the xy plane. So this part, the picture here, that's what's going to tell us r and theta. So we can see right away that when we're converting our bounds, that we're going to be able to figure out our r, theta, and z. Before we do that, I got a little bit ahead of myself because I'm just so excited to do the problems. We should deal with a function. X squared plus y squared in cylindrical coordinates, you should know that by heart. That's r squared. And dz dx dy, well, this is dA. Or sorry, excuse me, 3 dimensions dv. And so if I have dv, well, what do? I turn that into my cylindrical coordinates. That's going to be r dz dr d theta. Now the theta bounds, we're going all the way around, 0 to 2 pi. When I think about r, I go out from the center till I hit my bounds. Well, it's always to the circle. The circle has radius root 3, 0 to root 3. Now what about z? Well, for that, I look at my slice. And I say I come up, I start at z equals 1, and I stop at z equals square root of 4 minus x squared minus y squared. Converting z equals 1 into cylindrical coordinates is easy. Square root of 4 minus x squared minus y squared becomes square root of 4 minus r squared. And we're done. That's part A. If you wanted to, you could multiply r squared times r, but you don't have to. Now, part B, spherical coordinates. Now, the nice thing about spherical coordinates is the theta is still going to be the same, so that saves us a little bit of work. X squared plus y squared. Well, x squared plus y squared, we already said that's r squared, and in spherical coordinates, r is rho sine phi. So that's rho sine phi squared. So rho sine phi squared. Your dv becomes rho sine of phi, d rho d phi d theta. You just thought I did that in class. No, I do it all the time. Okay. Now, you could, if you wanted to, multiply these together, but if you're just setting it up, you don't have to simplify. If you were actually going to integrate, you'd combine these together. So theta, still the same theta bounds. That's easy to do. All right, now we have to think about our other two things, which are phi and rho. Well, for phi, we come off the positive z-axis, so I start at 0, because I'm already hitting my region, and I'm going to stop when I hit that point right there, the very corner. So I need to figure out that angle. So we have to sort of think for a second about where that angle is. So how do we find that? Well, what do we know? We know at that angle, that's going to correspond to the very edge of the circle. And the edge of the circle has root 3. So if we clean the picture up a little bit, so we went out distance root 3, we went up distance 1. So when we think about phi, we can say, I need the angle so that the opposite over adjacent, tangent of phi is root 3. Now, is there a nice angle where tangent of phi is root 3? And the answer is yes. It's one of those angles that we should hopefully know. It's pi thirds. Okay, so that's our angle. Now the picture, of course, doesn't look like pi thirds. Well, that's because it's not a great picture. But the math will save us. Now, what about rho? Well, you think about rho the same way you think about r in your polar coordinates. Start at the center and work your way. Where do you hit and where do you stop? So you have to say, where do you go in between? So we stop at the end. That's easy. That's at the sphere. That's sphere of radius 2. Rho is 2. We start at z equals 1. Well, z is rho cosine phi. So z equals 1 becomes rho cosine phi equals 1, or you get rho equals secant phi. And therefore, our integral will become 0 to 2 pi, 0 to pi thirds, secant phi to 2 of rho sine phi squared, rho squared sine phi, d rho d phi d theta. Find the center of mass of a thin rectangular plate cut from the first quadrant by the lines x equals 6 and y equals 1 if its density is given by delta of x, y is x plus y plus 1. So here, we're at x equals 6 and y equals 1. So it really is a very thin plate. Okay. And we also can say, well, what's true? Well, the density gets bigger in that direction. All right. Well, how do you find density? That's how you find density. You read it. How do you find mass? Well, you find mass by integrating density. So here it's a two-dimensional thing. It's a double integral dA over our region R. So here's our region R. And so in our case, no big surprises. It's going to become, say, 0 to 6, 0 to 1 of x plus y plus 1 dy dx. Okay, equals calc 1. All right, now the next thing is, what are your moments? Now you might say, wait a second, shouldn't we look for symmetry? Well, we should always look for symmetry, and there are some symmetries that might be candidates. Is this a good symmetry, we ask ourselves? And the answer is no. The shape is symmetrical, but if you look at the density, it's very dense over in the upper corner and very sparse in the lower corner. So because of that, it's not going to be symmetrical here. And I say, well, what about this line? Same problem. So this is one where, you look, there's no shortcut. You got to find everything. So that means we also have to find both of the moments. And now we look at the moment with respect to the x-axis. That'll be the integral over our region. And whenever we talk about moments, distance and density, so with respect to the x-axis, that would be y is our distance, and then x plus y plus 1 is our density. And we set up our integral 0 to 6, integral 0 to 1, of y times x plus y plus 1 dy dx, and it's calc 1 after that. No big surprises. These aren't hard integrals. You just have to be patient. No big surprises. Similarly, the moment with respect to y. Here, the distance is with respect to the y-axis, so that's x and x plus y plus 1 dA. You set up your integral, and off you go. Now, we're not going to find these integrals. You should try to do this problem. The final thing you do is once you have all these three, you get that your center of mass x bar y bar, that's m sub y over m, and m sub x over m. Just sort of check and ask yourself, is this reasonable? And if it's not reasonable, then you know you've done something wrong. Now, what do I mean by is it reasonable? Well, for one thing, it's a center of mass, so if your answer is out here, that's not reasonable. If anything, we should say it should be somewhere in the rectangle and biased towards the corner. And if it wasn't that, we should be like, okay, let's go double check our work. We have time. We can do our double check. Okay. Next example. Evaluate the integral over our curve C, sine of x squared plus 3x plus 5y minus e to the cosine x plus 2x plus log of y squared plus 1 dy. Automatically, when you see a crazy function, this is secret code for use the tools. We're not actually going to do the integral that they ask us to do. Instead, we're going to do something that allows us to answer this question. So if you see a crazy function or you see a crazy curve, it's a secret code for like, don't actually do what the question asks. Instead, be smart. And that's good. We know how to be smart. We've been taking classes in that. Being Smart 101. All right. Well, what is C? Well, we're told that C is some line segments. We go from 3, 0 to 0, 5 to negative 1, 0. So 3, 5, negative 1. And then here, this is at the point 2, negative 1. So I have, this is my curve. Now, if you ever see a curve which is closed up, you should automatically sort of, in your mind, say, oh, this is bounding a region. And you say, okay, so here I have a closed curve. I check the orientation. Is it good? Is it consistent? Am I such a way that as I move along the curve, that I'm always, my region is to the left, to the left? Yes, it is. Good. So it's the right orientation. So now I'm set up. See, this is closed curve, I think, Green's theorem. Okay, so that's our idea. We see a closed curve. We say, okay, there's the region. We're going to switch to Green's theorem. So what does Green's theorem say? Well, it says, if we think of this first piece as m, the second piece as n, then the integral over our curve of what we're asked to do is really the integral over the region of n sub x minus m sub y. All right. Well, that's the integral over our region, and just so I'll say explicitly, there's our region of, come here, take the derivative with respect to x, and that log y squared plus 1, which is terrible looking, goes away. You get 2. Come over here, take the derivative with respect to y. The sine of x squared plus 3x, terrible. E to the cosine x, terrible, but they're gone. But there's a 5. 2 minus 5 dA. So this is really negative 3. So the negative 3 comes out, becomes the integral over the region dA, which means you don't even have to do any integration. Because if you integrate 1 over a region, that's the area of your region. All right, well, if it's the area of our region, let's just use geometry. And geometry says, for instance, here I can think of this as 2 triangles. So there's a top triangle, and there's a bottom triangle. The top triangle, the base, this distance is 4, the height is 5, so that would be 1/2 base height. The bottom triangle, well, still 4, the distance, now we go down by 1, so that area is 1/2 base height. So I'm looking at area, so I'm not worried about part of it's above, part of it's below. I'm just looking for area. Area is area. And what do we have? Well, we get 10 plus 2 makes 12 times negative 3 gives us the final answer of negative 36. So Green's theorem, it should simplify. Now in this case, if you ever have something simplifying to just integrating 1, use geometry. But maybe it doesn't simplify to 1. But even if it doesn't, it'll simplify to something nice enough. that you can work with it. All right. You can already tell just by looking at this problem. You know we're not going to actually integrate that. No chance. No chance. But okay, a sawtooth curve C consists of 19 line segments, and we start at 0, 0, and we end at 1, 1. Okay, hopeless, hopeless. We're not going to do 19 different integrals. Okay, so find the value B, given that we have this big expression. All right, so what are we going to do? Well, we know we're not going to do the integral, which means we're really hoping for something to be true. In particular, we suspect that this should be conservative. All right, now, how do you find whether or not something's conservative? You can test it, but I like it. The better way is to say, look, let's just find the potential. So if we integrate the first term with respect to x, so integral negative pi sine pi x, that would be cosine of pi x. If we integrate the next term, 4 e to the 1 minus x arctangent y with respect to x, the 4 arctangent y is a constant. Integral of e to the 1 minus x would be e to the 1 minus x. I compensate for the minus x upstairs by dividing by negative 1, which makes the integral minus 4 e to the 1 minus x arctangent y. So that would be what I'd want to see in my potential function for that entry. For this entry, what would I want to see? Well, 1/2 by squared, that's the antiderivative. B is some constant, I'll figure that out. And then I have this other part. Well, now the e to the 1 minus x is the constant, and the antiderivative of 1 over 1 plus y squared. Well, I've hung out with myself too much to know that that's definitely going to be an arctangent. And lo and behold, we see that they're compatible in the following sense. The parts where the variables are shared, in other words, both x and y are in an expression, actually agree. So in other words, these line up. So it means that our potential function, f, that's cosine pi x minus 4 e to the 1 minus x arctangent y, and then plus 1/2 by squared. Okay, so there's our potential function. For full points, double check. So in other words, check the gradient, make sure it works out. Now, it's going to work if we've done our job right, but it also gives you sort of a sanity check. Did you do your job right? Did you goof on a sign somewhere? And so you go through and you find out, well, what happens when you take the derivative and you say, aha, everything works out, good, check. So we know it's now a conservative function, which means I don't need to know how many line segments there are. 19 line segments, 1 line segment, 1,000 line segments doesn't make a difference anymore. All I need to know is where I start and stop. And I already know where I start and stop because it tells us where we start and stop. So the integral along the curve becomes, of our stuff, we take our function f, evaluated at our endpoints, 0, 0, and 1, 1. So we plug in 1, 1. So we get cosine of pi, which is minus 1. Here we're going to get minus 4 e to the 0, arctangent of 1. We'll clean that up in a second, plus 1/2 b. We're going to subtract 0, 0. Cosine of 0 is 1. Then we're going to get minus 4 e to the 1, arctangent of 0, plus 0, because I have 1/2 b times 0. Now, certainly some things are true. 0 is certainly 0. Arctangent of 0 is 0. Arctangent of 1 is pi fourths. E to the 0 is 1. So we're going to get minus 1, which is minus 2. Minus 4 times pi fourths, which is minus pi plus 1/2 b. But wait, we were told this equals 5 minus pi. So we now say, okay, well that's great. We can conclude the pi's cancel. So minus 2 plus 1/2 b is equal to 5, or 1/2 b equals 7, which means that b is 14. And there's the answer, 14. Evaluate the integral from 1 to 2, integral 0 to 2 minus y, 2y cosine of x plus y cubed minus 3 times x plus y dx dy, by first making the change of variables. Ooh, a change of variables problem. meaning Jacobian. If you see a change of variables, it's going to be a Jacobian. And by the way, if we ask you to do a change of variables, we're always going to give you the variables. So the finding that what variables to substitute, you don't need to worry about that. Actually making the change, you have to worry. All right, so whenever you're doing a change of variables and they give you the change, you have to do a couple things. You have to worry about the Jacobian, you have to worry about the function, and you have to worry about the bounds. So we're just going to go through and do all those parts. So for the Jacobian, what is that? Well, I'm going to look at the Jacobian, which will be a function here of actually xy. And how do I find it? Well, I'm going to take the derivatives, u sub x, v sub x, u sub y, v sub y. And Jacobian is very, very forgiving. If you get things in a slightly wrong order, it'll almost always be correct. So u sub x is 1, v sub x is 0, u sub y is 1, v sub y is 2y. Take that Jacobian, we get 2y. Now what does this mean? Well, what this means here, the way you should read it, is if you see the Jacobian of xy, it says the Jacobian of xy times dx dy is equal to du dv. So, in our case, 2y dx dy is going to become du dv. Aha! I have a 2y dx dy. So, this part becomes our du dv. Great. That's good news for us. Now, that doesn't mean we're done. It just means step 1 is done. The function. Well, the function, I just have the part that wasn't absorbed into the Jacobian. And I want to write things in terms of u and v. Well, everything that's left really has x plus y. That means u. So the function becomes cosine of u cubed minus 3u. Okay, there's our function. Okay, so that's done. Oh, that was quick. Whew, I wish they were all that fast. Okay, now the bounds. Okay, so for the bounds, it's helpful to get a quick sketch of the picture. So we're going between 1 and 2, and we're going from 0, x equals 0, which is the axis there, out to the line 2 minus y. And this picture was actually in the test. So even if you have a hard time, a lot of times we actually provide the pictures. We're not testing you on picture drawing. That would be a fun test. Okay, so here we have our region, and it's good to mark the bounds. So y equals 1, and then we have the line x equals 2 minus y, which really is x plus y equals 2. Now the way I like to do this is once I know my bounding curves, I say to myself, let's rewrite the bounding curves using u and v. So, as an example, x plus y equals 2, well, that will become u equals 2. Y equals 1, well, I put in y equals 1, and here we see it becomes v equals 1. X equals 0, that's slightly more interesting. What does that say? Well, it says that u is equal to y, v is equal to y squared. If we put these two together, we say, aha, v is going to be u squared. So, in terms of our region, we have the following curves. So we go to the u, v plane. U is equal to 2, v is equal to 1, and then we have v equals u squared. So v equals u squared. Now, it may not necessarily be totally obvious which region to pick, because there's lots of pieces. You could say, well, could it be that part? And the answer is no, it can't be that part. Why? Well, you have to have all three of these curves have to bound your region. And you're like, oh, okay, all right. Well, how about this piece over here? All three of the curves bound the region, and no, wrong. Don't do that part either. It's not bounded. You look, you want the part where all three curves bound that region, and it's actually going to be a bounded piece, not something that blows up. And once you know that, it's easy to pick out the right piece. Okay, so that's our region. So we have, here's the curve v equals 1. We already have the curve u equals 2. And then we have our other curve v equals u squared. So what happens next? Well, we set up our integral. And now we have what? Well, we're going to integrate cosine u cubed minus 3u, and now comes the interesting point. See, this problem, depending upon how you do it, you have to pay attention to the order of integration, because order of integration matters, and it could get you in trouble if you do it the wrong way. So here, in our case, we want to say, look, should we integrate du dv or dv du? Now, in some sense, you could say, it doesn't matter if I'm just setting it up. Well, you're right. It doesn't matter if you're just setting it up. But if you need to actually integrate it, you have to think. So, looking at this, I don't want to integrate this with respect to u. So, I'm not going to. I'm going to integrate with respect to v first, because that I can actually integrate with respect to v. Look, the integral should be simple. If something's not simple, something is wrong, and you should swap the order of integration. In fact, that's a pretty common theme we're going to see probably 3 or 4 times on this next set of problems over the next little while. Swap the order. If what you have is terrible, don't do it. Be smart. Don't start. Okay, so where does u go from? Well, we intersect at 1, so u goes 1 to 2. And, well, where does v go? Well, v goes from v equals 1 to v equals u squared. Now, once you've integrated that, you'll see that's not a hard integral to do because the cosine u cubed minus 3u is a constant, and it's times v. That way v equals 1 to v equals u squared du. So that becomes 1 to 2 cosine u cubed minus 3u times u squared minus 1 du. Okay, well, how do you do this? Well, at this point, we're almost to the point where we say, and the rest is calc 1. Then to finish it up, we say, hey, what if you set the inside, I'm already using u, so I'll go 1 layer down, double u, going to double down, u cubed minus 3u. Then dw would become 3u squared minus 3 du, or another way we could say this is 1/3 dw is u squared minus 1 du. Now we're in great shape. This part will become 1/3 dw here, cosine of w, and then you'd update your bounds. So if you do that, you'll get the integral from, plug in 1, you get 1 minus 3, negative 2, plug in 2, 8 minus 6, positive 2 of cosine w dw. And here, it truly is calc 1 the rest of the way. Okay, so there you go. That one was good. A thin plate is composed of the points, x, y, that satisfy the inequalities x squared plus y squared is less than or equal to 9, as y, and y is greater than or equal to x. Find the mass of the plate if its density is given by density of xy is 2 square root of x squared plus y squared. Now, they're going a long ways out of their ways to obfuscate what we need. So let's unobfuscate. X squared plus y squared less than or equal to 9 means we're in a circle of radius 3. So here's our circle of radius 3. Y greater than or equal to absolute value of x. So I want to be inside the circle but above the absolute value, which means my region is a pretty generous slice of pie, a very good slice. Okay. But looking at this, we say, aha, this is set up for polar. But we kind of knew it was set up for polar because in polar, square root of x squared plus y squared is simple, 2r. So it's a polar problem. So if we want mass, mass is the integral over our region of our density dA. So we're going to integrate over our region. Density becomes 2r, and dA becomes r dr d theta. Well, where is theta? I go between my two angles that come from the absolute value. Theta is pi fourth, and over here, theta is minus pi fourth. So that's my theta, pi fourth minus pi fourth. And where do I go for r? Well, I go from the center out until I hit something. What I hit is this circle. It's a circle radius 3. So 0 to 3. And so, what do we have? Well, we can break this integral. In fact, we can pull it apart. Pi fourths to minus pi fourths d theta, and integral 0 to 3 of 2r squared dr. And then the rest of this is Calc 1. Nothing surprising after that. Okay, so really, what was this testing? Do we know how to find mass? And can we actually do polar coordinates? And can we convert to polar? So be ready. Be ready for polar, because we love polar. I should say, why do you love polar so much? Well, I think it's because you can have a fairly easy description of things. And so that's why we like polar. Evaluate the following line integral for the curve c equals e to the t squared minus t minus cosine of 2 pi t, comma, 2 sine of pi halves t squared minus t to the 9th. Now, we look at this curve. This curve, there's a good name for it. It's called terrible. It's a terrible curve. We'd never want to integrate along that curve if that was our real curve. So we say, okay, probably we're not going to have to integrate along our real curve because, oh, I'll bet you it's something that's conservative. And we say, okay, 2xy plus e to the minus x squared and x squared plus y cosine pi halves y squared. Okay, no problem. We just have to find the potential function. Okay, so you come here, integrate with respect to x. X squared y, well, that was easy, plus antiderivative of e to the minus x squared, which, oops, we don't know how to find the antiderivative of e to the minus x squared. Now, that's not to say it doesn't exist. We just don't know it. Okay, so we're going to have troubles finding the antiderivatives. Okay, so they seem to have thrown us a bit of a curveball here, but that's okay. Perhaps we can recover. Well, we can at least check that it's conservative. Okay, so how can we check? Well, what you do is if this is your m, and this is your n, you compare the following. M sub y, well, that's 2x. Well, it turns out that if you came over here and you did n sub x, you'd also get 2x, which means it's definitely conservative. So we know for sure it's conservative. We're just having a hard time finding the potential function. But we have a saving grace. We don't actually have to find a potential function. What we can do now is, since we know it's conservative, we can say, where do we go between? Let's figure that out. Okay, so we're in the plane. Where do we start? We plug in times 0. Let's see, we're going to get e to the 0 minus cosine of 0. That means we're going to have the x-coordinate is 0. Sine of 0 minus 0 to the 9th, which means we're 0. So we're starting here at 0, 0. And then we plug in 1. We're going to get e to the 1 minus 1. That's e to the 0. And here we're going to get minus cosine of 2 pi. That's 1. It's still 1. Oh, we're still at 0. Okay, well, how about this one? We're going to get 2 sine of pi halves. That's, well, sine of pi halves is 1, so that's 2. And then we're going to minus 1. Oh, so we're going to end at 0, 1. So the curve, I don't know, it's doing something. So they gave us this crazy curve. But now it's conservative. So what do? We say, I don't like your curve, nice mathematician teacher. I am going to pick a better curve. What's the better curve? Zoop. We're just going to go straight up. See, they chose a terrible curve. We don't have to go with it. So we're going to cross that curve out, and our curve is going to be 0, t. And it's still going to be 0 is less than t less than or equal to 1. Okay. So now we say, okay, we're actually going to do a line integral, but now we have a really simple one. So our bound becomes the bounds for t, 0 to 1. Everywhere where you see an x, put 0. Everywhere you see a y, put t. So the first entry, we're going to have 2 times 0 times t. Well, that's 0, plus e to the minus 0 squared, which is 1. So we're going to have 0 plus 1. Take the derivative of the x entry, which is 0, okay, plus, here we go, we get 0, plus t cosine pi halves t squared, and then derivative of the y entry is 1, and this is all dt. And we see, lo and behold, this becomes an integral. While not trivial, it's actually not too bad. t cosine pi halves t squared dt. So we set u equal pi halves t squared, du becomes pi t dt. Move the pi across, so you get 1 over pi. So then this becomes, what do we have? It's the integral 0 to 1. Well, it's going to become, plug in 0, you get 0. Plug in 1, you get pi halves, so 0 to pi halves. The t dt becomes 1 over pi du, and then we get cosine of u. And, oh, we're so close. This antiderivative of cosine is sine. Evaluate from 0 to pi halves. Sine of pi halves is 1, sine of 0 is 0, which means our final answer is 1 over pi. Good, good. So, this was from the final last semester. Fun problem. All right. Let D be the solid with 0 less than or equal to y, less than or equal to x, 1 less than or equal to x squared plus y squared, less than or equal to 9, and 0 less than or equal to z, less than or equal to arctangent y over x. It says see the picture. Well, I didn't have space for the picture, but the picture's not so bad. So we can actually kind of figure this out, even if we didn't have the picture. So 1 less than or equal to x squared plus y squared less than or equal to 9 means I'm going between two circles. Radius 1, radius 3. And then I'm told I'm between y equals 0 and y equals x. So that means my region here, if I think about it in the xy plane, that's set up really nicely. It's a sort of big wedge here. Okay, now we see this is going to work great in polar, and not too surprising. Hey, think about in cylindrical here. Now, that's in the xy plane. What is this looking like in 3 dimensions? Well, here I have the positive x-axis, so I'm starting, and I'm just sort of spinning around. So here's my base. So this part right here corresponds to that part. These match. Now what about this function, arctangent y over x? Well, we already are thinking in polar. So if we think of this in polar, we can say arctangent y over x is really arctangent of r sine theta divided by r cosine theta. The r's cancel. Sine over cosine is tangent, so you get arctangent of tangent, also known as theta, which means that what you have is kind of like a ramp, which as your angle increases, so here our angle is 0, as we increase, we're going to get our ramp is going to be higher. So we have this ramp coming down. So that's our shape. It's kind of like you take a wedge for a door, but then you've turned it, bent it out of shape. All right, well, here, now we see this is really well set up for our function. Our top curve is z equals theta. Our bottom curve, z equals 0. Sorry, I said curve, but I should say surface. So we go from 0 to theta, and we're set up for cylindrical. Okay, so we want to find what? We have the solid, given that we have a density function, we're after mass. So we're going to integrate over our solid, I'll call it d, of density dv. So that'll become the triple integral. I need to convert our density function into cylindrical. Well, how do you convert 3z into cylindrical? The answer is you write down 3z, because cylindrical involves z. So that was easy. dv, well, that's r dz dr d theta. Where does theta go from? Well, we're looking for theta and r, look in the xy plane. So we start at 0, we go to pi fourths, 0 to pi fourths. Where does r go from? Start from the center. So you hit the first curve, and you go to hit the second curve. So we go from 1 to 3. Where does z go from? From the bottom surface to the top surface, 0 to theta. And from here, the rest of this, it's Calc 1 type stuff. There's no surprises. The hard part about this one, setting it up. Setting it up. And once you set it up, straightforward. Compute the integral, 1 to 2, x squared to 8 minus x squared, 8x e to the y plus x squared squared minus 4 times y plus x squared dy dx. by first carrying out the following change of variables. Okay, another Jacobian one. All right, so let's see if we can get a handle on what this looks like. So what do we have? X goes from 1 to 2. So I have 1 to 2. Then I have some curves. Y equals x squared. Okay, so y equals x squared. It's going up. And y equals 8 minus x squared. Ooh, what does that look like? Well, if I had planned ahead better, what it looks like is it looks like this. In fact, you can see that they're going to meet at 2, because I'll have 4 and 8 minus 4. So that my shape is actually a sort of a triangular region in some sense. Okay. There was a picture given on this one, don't worry. We give you pictures. We like giving you pictures. All right. So we have that. So we can actually label some things. The left side, x equals 1. The bottom here, that's y equals x squared. The top, that's y equals 8 minus x squared. Okay, so what do? We go carry out the change of variables. So we're going to keep the Jacobian uv. We're going to take the u sub x, v sub x, u sub y, v sub y. So u sub x will be 2x, v sub x minus 2x, u sub y 1, v sub y 1. And we carry this out. We get 2x. Then we do minus minus 2x, which is 2x plus 2x, giving us 4x. So that tells us that 4x dy dx, or dx dy, doesn't matter which order, that's du dv. So we see here an 8x, so what should we do? Well, we're going to think it says 4x times 2. The 4x goes into our Jacobian, and then we have the rest of it. So we say, okay, so there's our Jacobian. Our actual function then, we have to change, that's 2e to the y plus x squared squared minus 4 times y plus x squared. Well, that's not hard to change because we know y plus x squared is u. So that's 2e to the u squared minus 4u. And, all right, so now the last part is the bounds. We've got to update the bounds. So we have to write the bounds in terms of our function. Well, so we have 3 curves. We have y equals 8 minus x squared, y equals x squared, and x equals 1. The first one becomes y plus x squared equals 8. Well, y plus x squared is u. So that becomes u equals 8. The second one, that's y minus x squared equals 0, which tells us that we get v equals 0. So we are in the uv plane. We have u equals 8. And so far v equals 0. So those are 2 curves. And then you have the line x equals 1. So what is that? Well, if you put in 1, we get the following. We don't have a snazzy way to do it, so we just say, well, what do the 2 equations become? We get u equals y plus 1, then we get v is equal to y minus 1. Or if we rearrange this, we could say, you know that y is equal to u minus 1, but it's also equal to v plus 1, which you can rewrite this now as your equation. We could say that v is equal to u minus 2. So that's a line that says we have an intercept at -2, and we just go up. So our region is that part that's bounded there. Okay. That looks right. Okay. Well, how do we finish it? Well, we have to set up our new function. So we're going to get an integral, our function, 2e to the u squared minus 4u. And the 4x dy dx becomes du dv. Now looking at this, we don't want to integrate this with respect to u, so we're going to integrate this with respect to v, dv du. So where does v go from? Well, v goes from 0 up until this intersection point. Well, where's the intersection point? Well, that's when u equals 8, so that means I'm going to go up to 6. So this is going to be 0 to 6. And now, where does v go from? Well, I'm going to go up until I hit this outer part, which is, oh, sorry, where does u go from? I'm going to go left to right. So the right is 8, the left is the curve. And so that's the curve u minus 2. And from there, it's algebra. Do I need to keep going, or are you convinced? There seems to be a question. Well,
So shouldn't it be from v equals 0 to v equals u minus 2?
well, if we're going with respect to dv, so the u bounds, where does u go from? U goes from, okay, where does u go? Oh, u goes from, I got the bounds wrong. 2 to 8, sorry. And v goes from, I think the u bounds are right. Is that the right? I'm nervous now. You're making me nervous. Don't make me nervous. Okay. You're throwing a lot at me right now. So what don't you like? Well, so let's see. If I fix u, I see. Okay, all right. Well, we're going. Yeah. Sorry, I was thinking of slicing horizontally. We should be slicing vertically. Yes. So fix u. Right. V goes from v equals 0. You are correct. Thank you. Up until we hit this line, which is u minus 2. Yeah. Yes. You're right. Okay. But the rest of that is Calc 1. Once you get your bounds right. If it doesn't work out right, by the way, go back and check. See, if I'd gone forward, I would have been like, darn it, this is supposed to work. And like, okay, got to go back and check. All right. So there's a lot of, we should have put these in a better order. We're going to do a lot of problems that are very similar to each other. Is the vector field conservative? Well, okay. That's a yes-no question. But, of course, it says to justify. Now, usually if you see a part A and a part B, there's a reason there's a part A and a part B. It's trying to say, maybe it helps to know it's conservative. Looking ahead at part B, we're doing a line integral, which means that there's two ways to tell it's conservative. You check partial derivatives, or you actually find a potential. So I'm thinking that we probably want to do find the potential, because that's going to be applicable for the next part of the problem. So what do we have? We have the 2x e to the x squared plus z, 1 plus e to the y, and x plus 2z. So the best thing to do is say, okay, if it's conservative, the first part is a derivative with respect to x, the second derivative with respect to y, and the third is a derivative with respect to z. So we say, well, okay, what should our function have? We take the integral with respect to x, we should get e to the x squared plus z times x. So we say our function should have that kind of thing. When we integrate with respect to y, we see we should have a y and an e to the y. And when we integrate with respect to z, we see that we should have an xz plus z squared. And what we're really checking for, are they compatible? In other words, when the things have multiple variables involved, they match up. Well, the only thing that has multiple variables is the xz, and they do match. So that means that it's going to be conservative. So what's our potential? Its f is e to the x squared plus, I'll put in the order xz, plus y plus e to the y plus z squared. I don't need both copies, I just need it once. Now, the check, take the gradient. And you check the gradient and like, woohoo, it works. Okay. So that's the justification that it's conservative. All right. Now that you know it's conservative, we say, hey, here's this terrible curve. Okay. All right. We know this game. Terrible curve, don't use it. So what do we do? Well, since we know it's conservative, we say, aha, this is going to be f evaluated at the endpoints. So the game is, where are your endpoints? So you plug in. So we plug in 0. 0 minus 1 e to the 0. Well, that's negative 1. So we start at negative 1 comma 0 plus cosine of pi halves, which is 0, times log of 1, which is also 0. Extra 0 we there. Then we have 1 to the 1 minus 1. So, okay, lots of zeros. Minus 1, 0, 0. Where do we end? Plug in 1. 1 minus 1 is 0. So 0 times e is 0. Then we get 1 plus cosine of pi halves, which is 0. Right? Yeah, 0. Yeah. And then log of 1. Whoops, I said before cosine of 0 is 0. No, cosine of 0 is 1, but that log of 1 is 0. And so that part is still 0. So we end up with 1. Okay, the last entry, 2 to the 2, which is 4, minus 1 is 3. So we go from negative 1, 0, 0 to 0, 1, 3. So our answer is what? Well, we plug f of 0, 1, 3, subtract f of minus 1, 0, 0. And when we plug in 0, 1, 3, we're going to get 1 plus 0 plus 1 plus e to the 1 plus 9, 3 squared, subtract e to the 1, that's e, plus 0 plus 0 plus 1 plus 0. So what happens? Well, what happens is our e's cancel, our zeros go away. We have a minus 1, which we can cancel. So the only things that are left are the 1 and the 9, giving us an answer of 10. All right. I imagine by this time, if you see a line integral, you're like, I'm not going to do a line integral. All right. Well, maybe not. Find the flux of the vector field 1/2 y, 1/2 x, z in the negative z direction, which means downward n, downward pointing, through the part of the surface z equals 4 minus x squared minus y squared that lies above the xy plane. So what do you have? Well, you have this surface, 4 minus x squared minus y squared. It's a bowl turned upside down. I just need the part of the bowl that's above the xy plane. So it keeps extending down, but I don't care about that part. So it's the surface that's above here. And if I wanted to, and I do want to, figure out where does it hit the xy plane, it hits the xy plane when I'm at 0 equals 4 minus x squared minus y squared, or x squared plus y squared equals 4. So in other words, as I look at the xy plane, this part right there, that tells me I'm at a circle of radius 2. Now, why do I say we want all this information? Well, when we're looking for flux through a vector field, our generic formula is the following. So if I want flux, this is going to be equal to the integral over the surface of minus m fx minus, whoops, sorry, let me fix that. Integral over the region, minus m fx minus nfy plus p dA. So let me be really explicit here. This is the flux through surface G, which looks like z equals f of xy over a region R with upward normals, and the vector field F equals MNP. This is a case where it's much shorter to write down the formula than to write down what the formula represents. Okay, so if you know your vector field, if you know your surface, and you want to find the flux, this is what you get. Now here there is one twist. The twist is we don't want upward, we want downward, which means our orientation's wrong. How do you fix orientation? Yeah, put a negative. Okay, so for our answer our flux is going to be the negative of the integral over our region R. So R here is our circle. This is R, whereas the surface, this is our surface, is the part that's above R. So we're talking about integral over R. So minus m, minus 1/2 y, times f sub x. F sub x is, I come to this part, f sub x minus 2x. Then minus n, so plus minus 1/2 x, times f sub y, which would be minus 2y. And then plus p. Well, plus p is plus z. But I don't want anything in terms of z. I want everything in terms of x and y. So initially I'll write z here, because I ran out of space. Okay, what do we have? The 1/2 and the 2's cancel. So I really have an xy and another xy. So this becomes minus the integral over the region of 2xy, and the minuses cancel out. The z we replace. So plus 4 minus x squared minus y squared. Okay, so that's what we have to integrate over our region. Now, how do we go about doing this? Well, here the key is where are we actually integrating? We're talking about integrating over our circle. It's a circle of radius 2. So this is now a polar integration problem. So we can go ahead and distribute the minus through. And, I'm going to do one little thing to save myself some time. We get a freebie part of this problem. That's going to be 0. Okay, so I'm not going to do that part. Now, you might object and say, why? Okay, great objection. Let's talk about that just for a moment. Okay, so if you come here, our R is a circle of radius 2. So I have a circle of radius 2, and I'm integrating over this region. So here's my region R. Now, if I look at the part that's 2xy, what I see is there's symmetry. So if I have a piece here, and I flip across and compare that piece, I see that I have the makings of a Teenage Mutant Ninja Turtle picture here. But the key here is to say, look at the contribution. If I compare the contribution over here versus the contribution over there, I'm flipping the sign. If you flip the sign, that means that one part, whatever it contributes, the other part will be the exact opposite in sign. Put the two together, you'll get 0. Now, if you do the integral, it's still going to be 0, but it's more work. So this is 0 by symmetry. Because there's a piece of it, we say, aha, if you flip across the x-axis or the y-axis, either one, it'll get cancellation. So we do this integral now in polar coordinates. I'll go ahead and put the minus sign through. The x squared plus y squared becomes r squared minus 4. If you're wondering why the sign changed, it's because I put the sign finally in. The dA, that becomes r dr d theta, and then theta goes 0 to 2 pi, and then r goes from 0 up to 2. And, well, let's finish the problem because there's a punchline here. So if we do this, we can break this into pieces, 0 to 2 pi d theta, and then we're going to have the integral 0 to 2 of r cubed minus 4r dr. And the first integral, well, this is 2 pi. The second one, this is 1/4 r to the fourth minus 2r squared, going from 0 to 2. Plug in 0, you get 0. Plug in 2, you get 1/4 times 16, which is 4. Then you're going to subtract 8. And 4 subtract 8 is negative 4 times 2 pi gives negative 8 pi. Okay, so there's the flux. Now, the punchline is we can do this problem now using the tools we have, but keep coming to class after the test. We're going to learn a really quick way to do this next week, but we can still do this one now. Find the integral of the function f of x, y, z equals x squared plus y squared plus z squared to the negative 3/2 over the region between the spheres of radiuses 2 and 4 centered at the origin. This looks like a terrible problem, but it's not a terrible problem if we do what? Well, if we think of it the right way. So, what's the right way? So what we have here is we have a small sphere. So we have a sphere of radius 2, and that's going to be put inside of a bigger sphere, which is a sphere of radius 4. So what are we getting? Well, we're trying to somehow capture what's in between the two. So this question is really trying to say, hey, can you realize that this is a spherical coordinate problem? So you should learn to recognize when to use spherical coordinates. Big clue. If you see a sphere in a problem, think spherical coordinates. It's kind of a dead giveaway. And so, all right. So what do we want? Well, so we want to do an integral over our solid shape here of x squared plus y squared plus z squared to the minus 3/2 dv. So this is going to become the integral. In spherical coordinates, x squared plus y squared plus z squared becomes rho squared to the minus 3/2. And then we have rho sine of phi. Okay, got to remember that. D rho, d phi, d theta. All right, theta. Well, where does theta go between? Well, the answer is I'm going to go all the way around. Because this picture, it's a full circle. So 0 to 2 pi. What about phi? Well, the answer is it's going to go all the way. Now, all the way for phi means 0 to pi. Because remember how phi works. Phi equals 0, straight up. And phi equals pi, straight down. And we only need to worry about that half. Now, you might say, what about the other half? The answer is you get the other half by also throwing in the spinning from theta. Okay, and where does rho go from? Well, 2 to 4. And now, this actually turns out to be pretty pleasant, because this rho squared to the minus 3/2 and this rho squared, well, it simplifies just to be 1 over rho. And then everything becomes a straightforward integral. So there's no surprises. You can integrate 1 over rho, that's log rho, evaluate from 2 to 4, and life is good. So this is one of the problems that, can you convert into spherical coordinates? And the answer is, yes, we can, with practice. Calculate the surface integral. So we have a surface integral of g of x, y, z equals the square root of x squared plus y squared plus the fourth over the part of the paraboloid z equals 9 minus x squared minus y squared above the xy plane. Okay, so this is a surface integral problem. Now, how do you do surface integrals? Well, the basic rule of thumb is that if you're doing a surface integral, and remember there's two kinds of surface integral problems. We've already done one of them. There's the flux and the surface integral. Know how to do both. Now, the flux one is the one you like, because the flux one, it doesn't involve square roots. Surface integrals involve square roots. So make sure you know which one you're doing. And cross your fingers and hope it's the one with the flux. Okay, so how do you actually do it? Well, you have your function that you're going to integrate, g of x, y, z, over your surface. I like to usually use g for surfaces, dsa. Now, this part is the square root of f sub x squared plus f sub y squared plus 1, dA. Okay. Now, there's one other thing that we need to know. It says the part of the paraboloid lying above the xy plane. You'll notice that we use the same shapes over and over again. We use paraboloids, we use spheres, we use cones, we use cylinders. And that's almost it. So you should be a little bit familiar with these shapes. You should know roughly what a paraboloid looks like. I really hope you know what a sphere looks like. You should know what cones look like. And all right. So here, it's a very similar shape from ones we've seen very recently. So this is our z equals 9 minus x squared minus y squared. So our surface is just the paraboloid itself. The region on which it's lying, down here, this is going to be a circle of radius 3. So here, our region R is a circle of radius 3. All right. Well, So what do we get? Let's clean up our DSA. So this is going to be the square root. Here's our f of xy. Square root of minus 2x squared plus minus 2y squared plus 1 dA. And so we get the following. We're going to integrate. We go now to our region R. We write our function all in terms of x and y. Well, in this case, it's easy because it was all in terms of x and y to begin with. Square root of x squared plus y squared plus a fourth. Then we have our DSA, which is the square root of 4x squared plus 4y squared plus 1 dA. Now, at first glance, this looks terrible, but on second glance, we say, wait a second, they're almost the same, because they're almost the same. If you factor out a 4, you get x squared plus y squared plus a fourth. And now the square root of 4 is 2, and they match. So what does this become? It becomes the integral over our region of 2 x squared plus y squared plus 1/4 dA. And now we're happy because we say, aha, this is not a bad integral. So we put things into polar. X squared plus y squared will become r squared plus 1/4. dA becomes r dr d theta. And our circle for r is radius 3, so that our bounds become 0 to 2 pi and 0 to 3. And the rest of the problem is Calc 1. So it's a matter of, do you remember how to do a surface integral? And once you have the surface integral set up, then you just follow your nose. Not so bad. You should also be suspicious. Look, if you're doing a surface integral, something has to give so that you can work with that square root. They have to either give you a strange function or something else has to occur. So, find. Now, if you ever see a problem that's this small, it's a dead giveaway what's going to happen. So if you see a problem that says, find this innocent looking integral, 0 to 4, square root of y to 2, x cubed e to the xy dx dy. This is highly suspicious. You know what's going to happen. It's a giveaway. Free points coming right now. So if you see something like this, this is a switch the order. Because all the problems that look like this on this point in the class, if they look this small, it means that you can't integrate the way it's been given to you. Which means the only way you can make progress is to switch the order. So secretly, this is a problem that says, switch the order, and then after you switch the order, miracles happen. All right, so that's what we're going to do. Now, how do you switch the order? This is, do you know how to read the bounds? So here, we're told that, for example, y goes between 0 and 4, and that x goes from square root of y up to 2. So, what does that mean? Well, we know what the line x equals 2 looks like. The line square root of y equals x can also be written as y equals x squared. We say, oh, well, that's a much easier way to see that. So square root of y equals x, and, x equals square root of y. It looks something roughly like that. And then we're going from 0 to 4. Well, 4 is up here. And so right now, it's slicing this way. It's horizontal slicing. So what we're going to do is we're going to switch it up. And we're not going to do horizontal slicing. We're going to go vertical. Okay. So integrate, integrate. We don't change the function. What we're changing is the order. dy dx. We look at where x goes from. 0 to 2. Then we say, okay, I know where x goes from. Where does y go from? Well, it goes from the line here. This is the line y equals 0 to the line up here, which is y equals x squared. So 0 to x squared. All right. Well, let's see if we can integrate that. Now, here, I should point out, you could have integrated this, but it would have been painful. You would have had to do integration by parts, and it would have given you something terrible. But now, we say, look, there's only a single y. That's why switching makes this more comfortable. And if you integrate this, what will happen is you have the x cubed. Integral of e to the xy is e to the xy, but you divide out by an x, because you think of it as e to the constant y. Remember, now treat x like that constant, so you divide out by that constant. And then we're going to evaluate from y equals 0 to y equals x squared and integrate dx. Now here, we get 0 to 2, x squared, and then when we evaluate, well, we're going to get e to the x times x squared, that's e to the x cubed, subtract e to the x times 0, which is 1. Well, you can take this, and this is an integral where it basically makes sense to say, let's just treat it as two integrals. It's absolutely okay to take an integral and say, let's just do the parts separately. Sometimes it makes sense to keep them together. Sometimes it makes sense to pull them apart. Because when's a time when you want to keep them together? Well, like when the inside is sort of like u cubed minus 3u. We saw one like that earlier. It says, oh, keep that together. But now it's like, oh, it makes sense to pull these apart. Now, what happens? Well, for the first one, this is going to be a calc 1, but it's good calc 1. U equals x cubed, and then du is 3x squared dx. Well, move the 3 across, and what do we get? This becomes integral of 0 to 8 of 1/3 e to the u du. So this is 1/3 e to the u from 0 to 8, which gives us 1/3 e to the 8th minus 1/3. The second integral, we don't even have to think very hard, minus 1/3 x cubed, evaluate from 0 to 2, and so what does this give us? Well, it gives us minus 8/3. So we get minus this expression, then the minus 8/3, so 1/3 e to the 8th minus 9/3, or minus 3. All right. Cool. That one was fun. I couldn't help myself. I wanted to finish that one. All right. Change the order of integration. Oh, okay. This one is more explicit. Oftentimes, we're not so explicit. Change the order of integration, and then find the exact value. So, well, we'll at least go through and set up the process. So, it's good to practice. All right, what do we know? Well, we know that y goes between 0 and 1, but the key here is what happens on the inside. So I'm going from the lines x equals y up to the line x equals y to the 1/3. Now, if you don't recognize these curves, rewrite them. So for example, y equals x, that I can recognize. The other one, maybe I'm not so good at that. X equals y to the 1/3, well, I cube it. And if I cube it, I get y equals x cubed, which means I'm coming in like so. And they intersect very conveniently at the point 1, 1. So currently, y goes from 0 to 1, and x goes from y to 1/3. So I'm doing horizontal slicing. Well, if I want to switch, I'm going to switch to vertical slicing, which means what? Well, integral, integral. The inside stays the same. 2x squared minus x to the 4th. I switch the order, dy dx. Where does x go from? 0 to 1. Where does y go from? Well, the bottom curve is x cubed. The top curve is x. So x cubed to x. Now, the first layer, easy to integrate, 0 to 1, 4 sine 2x squared minus x to the 4th times y, evaluated from x cubed to x dx. This is y equals x cubed, y equals x. So this becomes integral 0 to 1 of 4 sine 2x squared minus x to the 4th times x minus x cubed dx. Now at this point, this is a time when it doesn't make sense to break it apart, because we can kind of see what's going to happen. What we can see is that the inside, if we set u to that, because we always look for the inside when we're doing substitution. It's an inside job. So du would become 4x minus 4x cubed. Well, if we include the 4 here, I have a 4x minus 4x cubed dx, which means it's perfectly set up to become sine of u du. Then don't forget to update the bounds. So originally the bounds were 0 to 1, but now the bounds are going to be, plug in 0, Get 0 minus 0, which is 0, and plug in 1. 2 minus 1, which is 1. That's right. The old bounds were 0 to 1, but the new bounds are different, 0 to 1. And then from here, calc 1. Okay, good. That's good. I like switching the order. Let D be the hemispherical solid region described by x squared plus y squared plus z squared less than or equal to 1 and z greater than or equal to 0. Okay, so we have a hemisphere. It's a solid hemisphere, though. Okay, so it's a hemisphere. Let's see, what's the radius? Oh, it's a unit circle. Cool. Unit 1. Sorry, I said unit circle. It's unit sphere. So it's a solid sphere. And I'm above 0, so I'm sitting here on top of the xy plane. And my mass is given in a very clean way. 4 times the square root of x squared plus y squared plus z squared. Now, if you ever see the square root of x squared plus y squared plus z squared, that's almost a dead giveaway. This is rho in spherical coordinates. So we're already starting to think this should be a problem where we switch and do some spherical coordinate work. All right, so we want to compute z bar. Well, what is z bar? Z bar is the z coordinate of the center of mass. Now, they were being generous. They could have asked for the whole center of mass, and it would have been the same amount of work. Now, why would it have been the same amount of work? Well, there's symmetry here. So when you see that rotational symmetry, it's symmetrical about the z-axis. That means that the center of mass has to lie on the z-axis. So it's not surprising they asked for z bar. Everything else is free. So define z bar. You need to take the moment with respect to the xy plane and divide it by the mass. So we have to do two integrals. The mass, well, is going to be the integral of density dv over our solid. Now for us, since it involves a hemisphere, it just makes sense to switch into spherical coordinates. So our density is 4 rho. dv, rho sine of phi, d rho d phi d theta. You probably shouldn't sing it out loud. Maybe a silent like humming. It would be okay. But okay, all right. So there's that. And now what are the bounds? Well, full circle, 0 to 2 pi. That's good. Phi, well, start at 0, go to hit the xy plane. That means you went down pi halves. Rho, 0 to 1. Okay, no surprises. Now, when we're finding the moment with respect to xy, it's almost the same. In fact, the only thing that changes is what? Well, let's think about it. The thing that changes is you have to add on a z. In other words, it's a distance part. Now, you can't just put z, because that's not spherical coordinates. What you do is you convert it. So that becomes rho cosine phi. So you know that z is rho cosine phi, know that r is rho sine phi. You should be familiar with both of them. And then everything else is the same. So in other words, we still have the same density for rho. We still get rho squared sine of phi, d rho d phi d theta. Okay, good. And then there, nothing surprising. And we take the 2 and we divide and we get the answer. All right, so that's pretty straightforward. So let S be the solid, 0 less than or equal to x less than or equal to 2, 0 less than or equal to y less than or equal to 4, and 0 less than or equal to z less than or equal to z squared, and y plus z less than or equal to 4. Okay, well, that's a lot. Oh, but there's a picture. Okay, they gave us a picture. That's fantastic. Set up iterated integrals for the function, and now we just have to do it for particular orders. So setting up an integral. All right. Okay, so what do we do? Well, here's what I like to do, is when I'm thinking about how to set up integrals, I like to think of, this is an onion problem, classic onion problem. You have layers. You work through one layer at a time. And also, there might be some tears involved. But that's okay. We're going to do it. So what I like to do is I like to set up from the outside in. So if I'm doing it for part A, so I have a triple integral. And I'm going to have the function. And then I have dy, dz, dx. What it tells me is I'm going to do the y part last. So I want to start by looking down the y-axis. So I'm looking down the y-axis, and what do I see? It's almost like I want to cast a shadow on the y-axis. Well, I actually know exactly what I see, because I can see in this picture, what I'd see. So as I look down the y-axis, I'll see something in the xz plane. So what do I see in the xz plane? I see the following shape, x and z. I see here, that's x equals 2. That's this part. And then I see this curve. Well, that curve is there. Z equals x squared. So I have this line, z equals x squared. So that's the part I see when I look down the y-axis. Now, I'm ready to answer some questions. I say to myself, where does x go from? Well, 0 to 2. Well, that was easy. Good question. Where does z go from? Well, now I'm thinking of curves. See, when I ask where does x go from, what values? When I'm asking where does z go from, which curves? Well, the answer is z equals 0 to z equals x squared. So it becomes 0 to x squared. Now I think of the full picture. And I say, okay, now come back to the full picture. And I'm asking, so where do I go from, and I'm moving in the y direction. So I go from the back side, well, that's the xz plane, also known as y equals 0, to the front face. Well, that front face, this is the surface, y plus z equals 4. So I want to write this in terms of y equals, because it's a y bound, so y equals. So solving for y, you get 4 minus 4 minus z. There you go. That's part A. All right. So look down the axis, see what you have, and then work your way up. Now, part B. So part B, it's not just as simple as just jumbling. You got to work. You got to work. All right, so let's see what will part B become. Integral, 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 still function x, y, z. Now the order is dx, dy, dz. So the last thing I want to look at is the x. So what I'm going to start is I'm going to look down the x-axis. I'm looking down the x-axis, and what I should see is I should see a shape in the yz plane. And the shape that I'm going to see in the yz plane is this shape. It's a triangle. So that's what I'm seeing in the yz plane. And this triangle is the one formed by the line y plus z equals 4. So I intersect at 4, and here I go. Now I can start answering questions. So for instance, where does z go between what two numbers? Well, smallest value is 0, largest value is 4. 0 to 4. So that's easy. Now I say, well, what about, where does y go from? So y should go between two curves. So I'm going to go from the left curve. Now the left curve is easy. That's y equals 0. To the right curve. So I want to write y equals, in this case, 4 minus z. So I'm going to get 0 up to 4 minus z. Okay, good. Now, what's the last thing? The x. Okay, so now I want to say I'm in my shape. Where do I go from? Well, the answer is I go from the back curving surface. So there's this back curving surface here. I go from there and I move forward until I hit this triangular face. Now the triangular face, that's the plane where? Here it is, 2. X equals 2. The sloped surface on the back, what is that? Well, that comes from z equals x squared. So what do I need to do? Well, I need to say I'm going from z equals x squared, but I can't write z equals x squared. I need to write it as x equals. So it becomes x equals square root of z up to x equals 2. And that's the other bounds. All right, so practice. Look down an axis. Build your way up, one layer at a time. Remember, between two numbers, between two curves, between two surfaces. So that's what you should be looking for. Identify the right numbers, the right curves, the right surfaces. Okay, find the center of mass of points with 1 less than or equal to x squared plus y squared less than or equal to 4th, and y greater than or equal to 0, given that your density is equal to y. There's a lot of center of mass problems here. Well, we'll just quickly sketch what to do. 1 less than or equal to x squared plus y squared less than or equal to 4 says we have a circles here of radius 1 and 2, so our region looks like that. And y is greater than or equal to 0. Now, for a freebie, we know something. I should also say our density is y. We actually automatically know part of our center of mass. Our center of mass is going to be on the y-axis because there's symmetry here. Again, not just symmetry of our shape, but symmetry of our density, which tells us that x bar is going to be 0. All right, well, what's left to say? What's y bar? So y bar is going to be the moment with respect to the x-axis divided by the mass. So what are those integrals? So the moment with respect to the x-axis, the mass, we'll do the mass first. That's the integral over our region, density dA. It's dA because it's two-dimensional. So we integrate. We put everything in terms of polar, because this is definitely polar. Our density is y. So y in polar is r sine theta. So that's our density. And then dA, r dr d theta. Theta goes 0 to pi, because we only have the top half. R goes 1 to 2. And this is straightforward. The moment does something a little bit more. It has a distance. In this case, the distance is y. So you get y density dA. Well, the density is also y, so what you end up with is y squared. So 0 to pi, 1 to 2. So you get r squared sine squared theta. That's your y times density, r dr d theta. And here it's a little bit more subtle. You have to say, what can you do about sine squared? And the answer is power reduction. And once you do power reduction, everything else is straightforward. No surprises. Okay. So, my goodness, how many more do we have? How you doing? Hanging in there? Should we skip some of these center of masses? Let's see, is this a center of mass one? Find them. Yeah, let's skip the center of mass ones. There's too many center of mass ones. You can only go so far in a center of mass. Okay. So let C be the curve that goes from 0, 0 to 2, 0 to 2, 2, and then returns to 0, 0. Automatically here, the fact that we're returning, it tells you that you're going to start and stop at the same point. What that means is that we have a closed curve. So we went from 0, 0 to 2, 0 to 2, 2, back to 0, 0. So whenever I see a curve that's closed up, I say to myself, I'm going to be thinking Green's theorem, because Green's theorem is set up for curves that start and stop at the same point. So I'm thinking Green's theorem. All right, so what's the problem? Oh, we probably should see if it makes sense. Oh, it does make sense, because we're finding an integral along the curve of something which is absolutely terrible. We'd never want to actually find that. And some other stuff which is also looks absolutely terrible and we never want to find. All right, so Green's theorem says, lo and behold, if we think of this region R as what's been bounded, this is the integral over our region of n sub x minus m sub y dA. Again, for refresher, this is the m, this is the n. Now, n sub x, well, the good news is that's pretty easy to take derivative with respect to x. So that's going to be the integral over our region of y cosine y squared minus 1/3 y cubed. That's okay. Minus m sub y. There is no m sub y. It's 0, because the first term has nothing to do with y. Why did we even ask? Okay. So that's what we have to integrate. Now, it's still not a great integral. At least not yet. But we're not done. There's more to do. So what do we do? Well, now we have a choice. A choice has been presented to us. We need to integrate y cosine y squared minus 1/3 y cubed dA, where this is our area. This is our region. Well, looking at this, we don't have much of a chance of integrating this with respect to y. So we're forced, against our will maybe, to do dx dy, because we can't integrate with respect to y first. But we can integrate with respect to x first. Well, what happens? Where does y go from? Y goes from 0 to 2. The largest value is 2, the smallest value is 0. Where does x go from? Well, here we're going horizontal slicing. So we go from the line y equals x, or rather I should say x equals y, out to the line x equals 2. All right, well, what do you get? 0 to 2, y cosine y squared minus 1/3 y cubed, x evaluated from x equals y to x equals 2 dy, and you can probably guess where this is going. When you evaluate, well, you get cosine y squared minus 1/3 y cubed. You also have the y times x, so that's going to give us 2y, then y minus y times y, which is y squared. And now you can probably guess what's going to happen because you've seen this already. Namely, if you set this to be u, there's your du, and off you go. Okay, good. So that's not so bad. Green's theorem, make sure you choose the right order of integration, and life is good. All right, evaluate this integral. Integral 0 to 1, x to the square root of 2 minus x squared, square root of x squared plus y squared to square root of 4 minus x squared minus y squared, z squared dz dy dx, by first converting to spherical coordinates. Okay, so we have to convert to spherical coordinates. Now, it's good to sort of get a handle on what our shape looks like. Let's start by building it up. In the xy plane, what do we see? Well, we see here that x is going from 0 to 1, and then we're going from the line y equals x, which is that line, to y equals the square root of 2 minus x squared. Now, very conveniently happens to land there. So this is the y equals the square root of 2 minus x squared, which, if you rewrite this, this is x squared plus y squared equals square root of 2. So this is our region here in the xy plane. Now, if you go to 3 dimensions, well, what does this look like? What you have is you're going up in the y direction to square root of 2, because this is at square root of 2. And you come down. So this part here is this part over here. All right, but then we have our z. Z goes from square root of x squared plus y squared, which is a cone. So I'm going to a cone up until I'm going to hit a sphere. So z equals square root of 4 minus x squared minus y squared. Here I get z equals square root of x squared plus y squared. And I'm just going to spin the cone just a little bit, not much. Because if you look at it, I don't want to have the whole thing. I just want the part here that lies over that region there. So it's almost like, how should we think about this? If you can think of almost like an ice cream cone type thing where you then sort of cut off a small piece of it. All right. I don't know how good my artistry skills are. Again, for those of you who need help, there's my sphere, and then I have this nice flat straight thing. There's my cone. Okay, so now the question becomes, how do we switch things into spherical coordinates? Well, to switch things into spherical coordinates, it's helpful to understand a couple of things. First off, we integral. We have to convert the function z squared, but z is rho cosine phi, so we're going to square that. dz dy dx is dv, becomes rho sine of phi, d rho d phi d theta. Okay, that's not bad. All right, now theta. To understand theta, look in the xy plane. And where does theta go between? Well, the line y equals x, that's pi fourths. Here, the positive y-axis, that's pi halves. So theta is going to go from pi fourths to pi halves. Now, we've got to figure out rho and phi. But to do that, think of just taking sort of a cross-section here. So we take a cross-section, and what will we see? When we take a cross-section, whoops, sorry, that's r, this is z, we're going to see the top part of the sphere. This is the z equals the square root of 4 minus x squared minus y squared. And then we see the flat part of the cone. Z equals the square root of x squared plus y squared. Now, also known as z equals r. So here, it's not hard to read off the angle. So if I want to know where does phi go from, I go from straight up, and I come along, and I stop when I'm on this line z equals r. Well, that's a 45-degree angle. So here, I can see that phi is going to go 0 to pi over 4. All right, now that leaves us with rho. But rho, that's going to be easy, because we always think about rho as coming out from the origin. So we come out from the origin until we hit that bounding surface. In our case, the bounding surface that we hit is the sphere. Well, what sphere? It's the sphere of radius 2, because this sphere can be written as z squared equals 4 minus x squared minus y squared, or x squared plus y squared plus z squared equals 4. So rho goes from 0 to 2. Now, we're not done, but we're going to stop because there's no surprises here. Now we can integrate. In fact, if you look at it, it's not a very surprising integral at all. We can integrate the rho, so you got rho to the 4th, so you can integrate that d rho. If you look at your phi integrals, you got cosine squared phi sine phi. Well, you let u equal cosine phi, du equals sine, and off you go. You're in great shape. Okay, that looks really familiar. We did something close enough to that one already. Change the order of integration. Okay, that's a good one. There's always room for a good change the order of integration problem. So here we have a nice thing. So what do we have? X goes 0 to 1. That's easy to see. Y goes 0 to 1. That's not bad. And then we have z goes from 0 up to 1 minus x squared. Now, if we think about the shape here, so here's x, y, z. So I'm at the curve. Let's think about the surfaces here. The real key surface here is understanding this surface. Z equals 1 minus x squared. Now, to understand that, what you should do is you should say, let's start in the xz plane. So if I were to look in the xz plane, what would I see? I would see an upside down parabola. I only care about z between 0 and 1. I know that there's a part over here, but I only need to know what happens between 0 and 1. So I'm going to come down. So in the picture here, now I go to 3 dimensions. I'm going to translate that. So I start here, and I come down. Then that's just in the xz plane. What's going to happen? And the answer is you just translate that across, because there's no y dependence. Since there's no y dependence, you're always going to get the same picture. So our shape here is like you took a cube, but then you sort of sheared off one corner, rounded it off. So that's our three-dimensional shape. That's what we're going to integrate. Okay, so we want to change the order of integration. We don't actually have to solve things. That's good. So what are we going to integrate, change the order to? Integral, 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 and same function on the inside, whatever that is, dy, dx, dz. So now we start asking ourselves some questions. Well, if we want to understand things, what do? We're going to have y be the last thing that we deal with. Well, so if y is the last thing that we deal with, we're going to look down the y-axis. Well, we already know what happens when we look down the y-axis. We're going to see this shape. So here's what we see when we look down the y-axis. Well, that was really rather convenient. All right. So down the y-axis. And now we can answer some questions. Well, where does z go from? The largest and smallest values, 0 to 1. Now, suppose I know z, where does x go from? Well, I'm going to go from 0, which is this left-hand side, x equals 0, over to this curve. Now, this is the curve here, z equals 1 minus x squared, but I want to get it as x equals, because these are x bounds. So x squared equals 1 minus z, which means x is the square root of 1 minus z, the positive x. So 0 to the square root 1 minus z. And now, where does y go from? Well, I'm going to go from left to right. So I'm going to go from the back plane, which is the xz plane, y equals 0, to the front plane, which is y equals 1. So there's the updated bounds. This one's not so bad. The only thing that makes this one bad was we didn't give a picture. Nowadays, we're better at drawing pictures, so we like to give pictures and make more interesting integrals. All right, rewrite but do not evaluate. Oh, our favorite thing, we don't have to evaluate. The following iterated integral using a change of variables. Okay, so good change of variable problem. All right, so let's see what we have. Well, this could be interesting. Okay, so let's do our Jacobian. U equals y, v equals x minus y plus y squared. So our Jacobian, in terms of xy, so u sub x, v sub x, u sub y, v sub y. Well, u sub x, 0. V sub x, 1. U sub y, 1. V sub y, lots of stuff. And take this determinant, we get -1, but of course we turn that positive, so our Jacobian is 1. That means our scaling factor is 1. Well, what does that mean? Well, it says that Jacobian of xy dx dy is du dv, or, because we get 1, dx dy is du dv. So that means that's easy to switch the dx dy part. Just becomes du dv. What about the function? Well, the function, that's not bad. Why? Well, x minus y plus y squared, that's v. So let's update where we are. dx dy becomes du dv. Then our function, 1 over 1 plus x minus y plus y squared becomes 1 over 1 plus v squared. Okay, well that was, so far, pretty easy. What's the part, that's going to be tough? Well, probably the bounds. So we got to think about those. So what can we say about the bounds? So here, we're going y from 0 to 1, and then we're going y minus y squared equals x, or less than or equal to x, less than or equal to y. All right. So y equals x, or x equals y. That's a pretty simple curve. Now y minus y squared equals x. That one maybe not so simple. So x equals y minus y squared. But you can check a couple of things. When y equals 0, you get x equals 0. When y equals 1, you get x equals 1 minus 1 is 0. Oh, okay. So we're back to 0. Maybe another point, a half. So if you plug in y equals a half minus a fourth would be a half. So it looks like it's doing something like this. All right, so that's our rough shape. So here's our x equals y minus y squared. Here's our x equals y, and we're doing something like that. So our three bounding curves that we need to figure out what to do with, x equals y minus y squared, and then the top part here, y equals 1. Well, let's just go through them. Y equals 1. That's not bad, because we know u equals y. So u equals 1. That was easy. Here, we can rewrite this as x minus y plus y squared equals 0. And we have x minus y plus y squared. So that becomes v equals 0. And then x equals y. Well, that's not so clear. But let's see what happens if we plug in x equals y. We have from the first term u equals y. From the second term, we get v is x minus y, but that goes away. So v equals y squared, which tells us that we can say that v is equal to u squared, because we can substitute y equals u. So, in terms of our pictures here, if we're looking in the u, v plane, we have v equals 0, u equals 1, and v equals u squared. Okay, so that's our shape. That's our region. So now we're ready to put it all together. Integral, our function, 1 over 1 plus v squared. Our Jacobian, dx dy becomes du dv or dv du. We'll do dv du. Why not? Doesn't really matter. Just pick one. Where does u go from? U goes from 0 to 1. And then where does v go from? Well, I go from v equals 0 to v equals u squared. So 0 to u squared. And I'm ready. Away I go. Away I go. But I don't actually have to integrate this. You can. It's not a bad one. In fact, it's a rather pleasant integral to do. All right, center of mass. Well, we're going to skip the center of mass one. Okay. Ooh, this one's fun. You find yourself in outer space trying to get to a passing ship. Out of other alternatives, you put a small puncture in your glove to have some of your remaining air escape. That will then propel you forward to bridge the remaining short distance to the ship. Your trajectory can be modeled by a curve in 3 space. T cosine 2t, t sine 2t, 4/3 t to the 3/2, where time goes between 0 and 1. Given that the amount of oxygen you use at any given point along the curve is something, that's a function, 1 minus 9/16 c squared, units per distance. So in other words, you're using up your oxygen, and that tells you how much. In some sense, you can think of this as almost like a density. Well, how much oxygen did we use? That's the question. And we're going to use a line integral to find the answer. In some sense, it's almost like you're looking for a mass, and we have a density. And the reason we say in some sense is because you are. So that's why it is. It's just a matter of interpretation. So what is this question here? Well, what this question really is the following. It says, what is the line integral of 1 minus 9/16 z squared ds? So this is the rate per distance. So units per distance. So units per distance times distance, that's how much you're using at any given point. And you want to add up the total, that's the integral. Okay, cool. So this isn't, there's no conservative functions, there's no potential function. This is a straightforward line integral, old school. So what do we need to do? We need to find our ds. So that's the square root x prime squared plus y prime squared plus z prime squared. Okay, dt. So for us, that becomes x prime. Well, what's that? Take the derivative. T cosine 2t, product rule. So cosine 2t minus t sine 2t squared plus, go to the next one, product rule. Sine of 2t plus t cosine 2t squared plus, go to the next one, 4/3 times 3/2, because we're going to multiply, bring the power down. 4/3 times 3/2 will give us 2 t to the 1/2 squared. Okay. And then there's a dt, which I can't quite fit on the end. Cool. Well, we've been looking for a chance to work out our algebra skills. Here we go. Woo! We're going to run out of space. Cosine squared 2t minus 2t cosine 2t sine 2t plus t squared sine squared of 2t. That's just if we square the first one. Well, we're running out of space, so we'll put some next one underneath. Sine squared 2t plus 2t cosine 2t sine 2t plus t squared cosine squared 2t plus 4t on the end. All right. Well, let's hope something nice happens. Well, you should always be suspicious. Nice things should happen. Those cancel. Cosine squared plus sine squared becomes 1. T squared sine squared plus sine squared becomes t squared. So, square root of 1 plus 4t plus t squared, which makes me think I've copied something incorrectly. Well, sorry, what? Oh, you're right. You're right. There's a 2. This is really 8. There's a 2. Oh, man, okay. There's a plus a bunch of 2's. Okay. So, a lot of 2's. There's a lot of 2's. Which ones have 2's? There's a 2 here. There's a 2 there. Thank you. Thank you. So if things don't work out right, you know you made a mistake. And then, of course, hopefully you don't have to do it in front of hundreds of people. So that, no, this was fine. This is just cosine. This one was a 4. That was a 4. They still cancel there. So this is still a 1. There's a 4t. And then there's a 4t squared. Okay, good, good. Now, we should have been suspicious. It wasn't working. We were. This is a lot less suspicious. Why? Well, they set it up to be nice for us. This is 1 plus 2t quantity squared. So we get 1 plus 2t. And then all along we've been forgetting to write the dt. So what do we end up with? So this becomes the integral 0 to 1, because we write in terms of t, 1 minus 9/16 z squared. We replace that by 4/3 t to the 3/2 squared. And then ds becomes 1 plus 2t dt. And you can clean this up before you integrate. Integral 0 to 1, 9/16, this becomes 16/9, so those cancel. You get 1 minus t cubed times 1 plus 2t dt. From here, it's calc 1. So you distribute everything through and integrate the parts, and you get your answer. All right. Rewrite the following as a single integral by changing the order of integration. So, okay, so we have 3 integrals. Integral 0 to 1, integral negative 1/2 square root of 4 minus y to negative square root 1 minus y, f of xy dx dy. Then integral 1 to 4, negative 1/2 square root of 4 minus y to 1/2 square root of 4 minus y, f of xy dx dy, plus integral 0 to 1, square root of 1 minus y, 1/2 square root of 4 minus y. Wow, interesting. Okay, well, challenge accepted. A single integral, one integral to bring them all, one integral to find them, one integral. All right, how are we going to do this? All right, well, let's think about the curves. Probably it'll help for us to identify these curves. So we have x equals minus square root 1 minus y. Well, let's rewrite this. This becomes x squared is 1 minus y, or y is 1 minus x squared. So if we were to sketch that, y equals 1 minus x squared, that's easier for us to sketch. We start at 1, and we come down, and we intersect here at 1. Now, the other curve here, this is x equals minus 1/2 square root 4 minus y. Okay, well, move that across. We can say minus 2x is equal to the square root of 4 minus y. You square both sides. 4x squared equals 4 minus y. Or you could say y is 4 minus 4x squared, which means I come up here to 4, and I'm coming down, and it just so happens that when x equals 1, I happen to know that I intersect here at 0. So, similarly, I can see on the other side, I'm going to do the same thing, but with the plus. Well, the plus is that we'll get the same curves on the other side. And now, staring at this for a few minutes, we can start to see what's happening. This first integral here, we're going from 0 to 1, and we're going between these two lines. So this is integral number 1. The second integral goes from 1 to 4, but now we're going between these two curves. So we're going here with integral number 2. We have this region here. And the last integral is, the third integral is on the other side. It's this part over here. So this is the third integral. And so I say, okay, all right, well, we had to split into 3 integrals because we always had different left and right. So now, what's our one integral? Well, we're going to swap the order of integration. F of xy now becomes dy dx. Where does x go from? Whoops, I got my signs wrong. -1 to +1. Well, where does y go from? It goes from this bottom curve, 1 minus x squared, to the top curve, 4 minus 4x squared. And that's it. That's one integral. And looking at that, I can say, well, test long and prosper.